Chapter 19. The hydrogen atom and hydrogenic ions. Section 19.2. The wave functions of the hydrogen atom. The kinetic energy of the nucleus being neglected. The Schrödinger equation of the hydrogen atom is approximately H psi equals E psi, where H is the kinetic energy operator of the electron and the attraction felt by the electron. This is the Laplacian operator, which is the sum of the second derivatives in the x, y, and z direction. This Laplacian can be expressed in the polar spherical coordinates r, theta, and phi. It's impossible to solve the Schrödinger equation if we use the x, y, z coordinates, because we have this 1 over r on the bottom over here, and this 1 over r is equal to 1 over the square root of x squared plus y squared plus z squared. When we solve differential equations such as the Schrödinger equations, it's very important to be able to separate the variables. But now if you see this square root of x squared plus y squared plus z squared, we know it's impossible to separate x from y or z. Therefore, we have to solve the Schrödinger equation in the spherical polar coordinates like this. Now we have only r, theta, and phi. How do we solve this? Well, first, we want to simplify this equation a little bit. This Schrödinger equation, can be simplified when we use the atomic unit system, in which the charge of the electron is defined to be 1 atomic unit of charge. The mass of an electron is defined to be 1 atomic unit of mass. H bar is defined to be 1 atomic unit of angular momentum, and 1 over 4 pi epsilon 0. This is the electric force constant. It's also defined to be 1 atomic unit. Now if you look at SI units, the charge of electron is 1.6 times 10 to the power negative 19 coulomb. The mass of electron is 9.1 times 10 to the power of negative 31 kilogram. H bar is roughly 10 to the power of negative 34 joule second. And this electric force constant, 1 over 4 pi epsilon 0, is about 9 times 10 to the power of 9 joule meter per coulomb squared. Now, if we use the atomic unit system, this h bar squared becomes 1. The mass of the electron becomes 1. The charge becomes 1. And this 1 over 4 pi epsilon becomes 1. So again, this is the Schrödinger equation for the hydrogen atom in SI units. It's awfully complicated, but in the atomic unit system, the equation is at least somewhat simplified, because h bar is 1, the mass of electron is 1, the charge of electron is 1, moreover 1 over 4 pi epsilon 0 is 1. Now we have a slightly simpler equation for the hydrogen atom. The use of atomic units makes the derivations also easier in quantum chemistry. The units of other physical properties may be expressed in terms of the 4 fundamental atomic units. For example, 1 atomic unit of energy is called 1 Hartree, denoted by E sub h. It's defined by this mass of electron times the charge to the power of 4 divided by 4 pi epsilon 0 squared and h bar squared. Again, the 4 fundamental atomic units are the mass of the electron, the charge of the electron, h bar, and 1 over 4 pi epsilon. So now we have the atomic unit of energy. It's about 4.36 times 10 to the power of negative 18 joule. We can also have the atomic unit of length, which is 4 pi epsilon times h bar squared divided by me times e squared on the bottom, and it's roughly 5.29 times 10 to the power of negative 11 meters, or 0.529 angstroms. 1 angstrom is 10 to the power of negative 10 meters. Now, when two electrons are separated by one atomic unit of length, the repulsion between the two electrons is plus 1 atomic unit of energy. If one electron and one proton are separated by one atomic unit of length, the attraction is negative 1 atomic unit of energy. Again, the Schrodinger equation in atomic units is this. First, we apply the kinetic energy operator to psi, and then the potential energy operator to psi. The potential energy operator is negative 1 over r only because the charge of the electron is 1. 4 pi epsilon is 1. Now we're going to solve this equation. Solving this differential equation can be non-trivial and tedious. So we will simply present the solutions here. As long as we can verify the solutions, we're good. The wave function of the electron may be expressed as the product of two functions, a function of r and a function of theta and phi. The function of r is denoted by uppercase R. The function of theta and phi is denoted by y. So in this R, we have two quantum numbers, n and l. We need n and l to determine the form of the function r. And over here, y is determined by two quantum numbers as well, but this time quantum number L and its z component quantum number m sub L, or so-called magnetic quantum number. The wave function is the product of the radial function and the this part is the angular function. So the radial function of r depends on both n and l. N is the principal quantum number, L is the angular momentum quantum number. L can be from 0 to n minus 1. In this y function, the angular function of theta and phi depends on two quantum numbers. One is this L, the angular momentum quantum number, and m sub L, which is the magnetic quantum number. M sub L multiplied by h bar is the z component of the angular momentum. And again, the expression of this angular function y depends on both L and m sub L. Other than n, L, m sub L, the electron in the hydrogen atom, or any electron, has two more quantum numbers, s and m sub s. S is the three-dimensional spin angular momentum quantum number. M sub s denotes the z component of the spin angular quantum number, or it's called spin quantum number. The value of s is always 1/2. The value of m sub s can be plus or minus 1/2. Now let's look at the wave function of the electron. It's always a product of the radial function of the radius and the angular function of theta and phi. Now let's look at a few radial functions. For example, the 1s orbital, we have n equals 1, l equals 0, and this is the function, a normalization constant times e to the power of negative r over a naught. A naught is one atomic unit of length. A naught equals 0.529 angstroms. Now 2s orbital, again a normalization function, a polynomial function, an exponential function. By looking at this, we see a spherical node. When r is equal to 2 times a0, this wave function becomes 0. Therefore, we have a spherical node at r equals 2a0. And 2a0 is simply 2 times 0.529 angstroms. And now we have an exponential function. This time it's e to the power of negative r over 2a0 compared to e to the power of negative r over a0. We have this 2p radial function. So again, normalization factor and then polynomial function. This is just first order. And now we have this exponential function. So 2s and 2p share the same exponential function. Now let's look at 3s, 3p, and 3d. They share the same exponential function. e to the power of negative r over 3a naught. Same here and same here. But if you look at the polynomial function, they're different. Over here, we can set this polynomial function to be 0 to obtain the two spherical nodes for the 3s orbital. And over here, we can set this to be 0 to find the one spherical node of the 3p orbital. Obviously, we can look at this and see, well, r is equal to 6 times a naught. We're going to get the 36 here and 36 here. 36 minus 36 is 0. So when r is equal to 6 times a naught, this function becomes 0. We have a spherical node. Now over here, we do not have any spherical node. In atomic units, the first few normalized radial function of r are this. They look a little simpler. So 1s orbital has a exponential function e to the power of negative r. 2s 2p e to the power of negative r over 2. 3s 3p 3d e to the power of negative r over 3. And now if you look at the polynomial function of r over here between 2s and 2p, there's some difference. Over here, you have a spherical node when r equals 2. Over here, when this second order quadratic function of r is 0, you can find two roots that correspond to the two spherical nodes of the 3s orbital. Here, when r is 6, we have a spherical node. Over here, we do not have any spherical node. How do we solve this? Well, it's pretty easy. If you remember how to solve the quadratic function, it's negative b over here, negative b, so it's going to be negative 18 plus minus the square root of b squared minus 4ac. That means the square root of 18 squared minus 4 times 2 times 27, and then divided by 2a. That means divided by 4, and you get these two roots, 1.9 atomic unit and 7.1 atomic unit. These two are the two spherical nodes for the 3s orbital. In atomic units, the first few functions of r are as follows. These functions are normalized. Well, we can double check this. If you use Wolfram alpha, you can just enter this, integrate, this thing from 0 to infinity. So what is this? Well, this is simply this function squared, and then multiplied by r squared. If you integrate this whole thing, you'll get 1. In spherical coordinates, the volume element is r squared sine theta dr d theta d phi. Therefore, when we normalize this function, we need to take this function squared over here, and then don't forget we have r squared and then dr. So we have this equals 1. R is from 0 to infinity. Meanwhile, the angular function of theta and phi must also be normalized, and we have this integral here. Theta is from 0 to pi, phi is from 0 to 2 pi. The reason we have this sin theta here is because it's part of the volume element. Now the first few angular functions are the solutions to the three-dimensional quantum rotation of a two-body system, something like this. The first one is just a constant, and that's not surprising because s orbitals do not depend on theta or phi, so it has to be a constant that does not depend on theta or phi. Now let's look at p orbitals. When you look at p orbitals, well, the solutions are this: cosine theta, which is z over r, or sine theta times e to the power of plus minus I phi. Remember, e to the power of plus minus I phi are cosine phi plus minus I sine phi. So really, we're looking at a linear combination of x plus minus iy over r. Sine theta cosine phi is proportional to x. It's x over r. And sine theta sine phi is y over r. Now let's look at tz squared. dz squared is proportional to 3 cosine theta squared minus 1. So it's actually 3z squared minus r squared over r squared. And because r squared is x squared plus y squared plus z squared, here on top it's equivalent to 2z squared minus x squared minus y squared. Now we have dxz plus minus I dyz. they can be expressed as sine theta cosine theta times e to the power of plus minus I phi, which can be expressed as xz plus minus I times yz over r squared. And now we have dx squared minus y squared and dxy. The linear combinations of these two can be written as this. You have sine theta squared times e to the power of plus minus 2I phi. E to the power of plus minus 2I phi are linear combinations of cosine 2 phi and sine 2 phi. So we can look at sine theta squared times cosine 2 phi. That's equivalent to x squared minus y squared over r squared. Sine theta squared times sine 2 theta is equivalent to 2xy over r squared. We can easily verify this function y00 is normalized. We just need to integrate this. The squared modulus of y times sine theta d theta d phi. The integral is 1. The wave function of the electron of the hydrogen atom may be expressed as the product of a function of r and another angular function of theta and phi, so like this. So we're going to do the multiplication. The 1s orbital is the function of r and the function of theta and phi. So we put this together, we get a normalization constant times e to the power of negative r. Now 2s orbital, the function of r, the function of theta and phi, we multiply them together, we get a polynomial function of r times a exponential function of r. 2p orbitals, 2p0 over here, 2p0 and 2pz are the same thing. It's proportional to z and e to the power of negative r over 2. Now 2p plus minus 1. So what does that mean? Plus minus 1 means m sub l is equal to plus minus 1 when L is 1. And these two orbitals are neither px or py. They are linear combinations of px and py orbitals. So 2p plus minus 1 can be expressed as a normalization constant times x plus minus iy times the exponential function of e to the power of negative r over 2. Again, these two are linear combinations of px and py. And conversely, 2px and 2py are linear combinations of 2p plus minus 1. The wave function of the electron of the hydrogen atom may be expressed as the product of a function of r and an angular function of theta and phi, so like this. Now let's look at this 2p plus minus 1. That can be expressed as this. Now we're going to take the linear combinations of these two. So first we can add up 2p1 and 2p minus 1 divided by the square root of 2. We get the expression for 2px. Now we have similarly the expression of 2py, the same normalization factor times y times e to the power of negative r over 2. What about 2pz? Well, you just need to replace this y, you get 2pz. 1 over 4 times square root of 2 pi times c times e to the power of negative r over 2, that's 2pz. So you can see this 2pz over here. The 2p plus minus 1 wave functions are eigenfunctions of the z component of the angular momentum operator. The corresponding eigenvalues are plus minus h bar. The corresponding eigenvalues for 2p0 or 2pz is just 0 when m sub l is 0. Now the 2px and 2py atomic orbitals are expressed as real functions, which are more tangible than complex functions. However, 2px, 2py atomic orbitals are not eigenstate of the z component of the angular momentum operator, so that means we cannot determine the value of the momentum in the x and y direction. However, we can determine the z component of the angular momentum and also the total angular momentum at the same time. We can, however, determine the 3D plus minus 1 wave function and their z component. It's plus minus h bar. They are linear combinations of 3D xz and 3D yz orbitals. The 3D plus minus 2 wave functions are linear combinations of these two orbitals, 3D x squared minus y squared and 3D xy. So again, plus minus 2 means m sub l is equal to plus 2 or minus 2. If we combine these two wave functions, we can get 3d x squared minus y squared and 3d xy. So now let's look at the shape of some of the functions. Again, the 3s orbital is a exponential function multiplied by a second order polynomial function of r. And we have two roots here. That means we have two spherical nodes. And we also have 3p orbitals. They have one spherical node when r equals 6. So that means we can see a spherical node over here when r is equal to 6. And we have a planar node. When x is 0, y is 0, z is 0, we see a planar node in the 3px, 3py, 3pz orbital. And now look at the 5 d orbitals. We have 5 different d orbitals. They all each have two nodes, but different shapes. To normalize these wave functions, we need to solve the following equations. The integral of the squared modulus of psi times the volume element should be 1. R is from 0 to infinity, theta is from 0 to pi, and phi is from 0 to 2 pi. So again, we can examine those wave functions to see where the nodes are. So over here, when x squared is equal to y squared, we have two nodes. When x is 0, we have one node. When y is 0, we have node. Similar here, we have two planar nodes. When y is 0, z is 0. When x is 0, z is 0, we have two nodes. Over here, it's a little bit more complicated. When 3z squared is equal to r squared, we have actually two nodes with a cone shape. Now finally, let's look at the orbitals over here. The first few wave functions of the hydrogen atom are shown below. Each atomic orbital has n-1 nodes. That includes n-l-1 spherical nodes and L planar or angular nodes. For example, in a 3p atomic orbital, there are 3-1-1 spherical nodes. We just use this equation. When n is 3, L is 1, well, we have 3 minus L-1, that's one spherical node, and one planar node. In the 3D z squared atomic orbital, there are two cone-shaped angular nodes when cosine theta squared is equal to 1/3. What does that mean? That means when z over r squared is 1/3, or when z over r is 1 over the square root of 3. Now in the 3D xy atomic orbital, there are two planar nodes, x equals 0 and y equals 0. So now let's look at this. This is the 3D z squared orbital. I want to show you two conical nodes. One is here, one is here. They correspond to cosine theta is equal to plus minus the square root of 1 over 3. So that's why you have a cone with a constant theta. And over here you have another cone with a constant theta. Because cosine theta can be plus minus square root of 1 over 3, you have two cones as the nodal surface of this 3D z squared. Now let's examine the spherical nodes of the s orbitals. One s orbital has 0 spherical nodes, 2s orbital 1 spherical node, 3s orbital 2 spherical nodes, and 4s orbital 3 spherical nodes. 2p orbital, no, we do not have any spherical nodes, but we have a planar node. Over here, 3p orbital, we have a planar node and 1 spherical node. Alright, 4p orbital, we have 1 planar node and 2 spherical nodes. So we can see the trend is this. Each atomic orbital has a total of n-1 nodes. And among this n-1 nodes, we have n-l-1 spherical nodes and L planar or angular nodes.